Morning, everyone. Our session gonna start shortly, and right now we're just waiting for additional students to join the session. And then for the speakers, one I'm gonna be able to there should be a set agenda, updated agenda that is updated to can we share an updated agenda somewhere? I think it was sent out to the student this morning, and when it is your turn, and you will be able to share your screen from your side, and any question will be here. So here is the updated agenda in the Google Doc document in the chat window. So total, we have 16 talks this morning. Okay, maybe let's get started. So welcome back, everyone. So this is our final plenary session, and we will have 16 students to give presentation about the work they have done throughout this course. And so before we start to introduce our first student, and I would like to also send a reminder that for those of you who decide to receive a course credit, please submit your final presentation regardless of whether you presented today or not. Please submit your final presentation through Moodle, and that's the only way for you to receive the course certificate after the course. So let's get started. So our first speaker is Subathra A. And Subathra, are you here? I think she was here earlier. Let's see.
Yes, ma'am.
Yeah, yeah. Could you share your screen and we will get you started.
Okay.
Yeah. So, and her talk is on InSAR analysis of a Calvi basin using Sentinel-1 data.
Hello everyone, I am Subathra. Today I will be presenting my InSAR analysis on Kaveri Basin using Sentinel-1 data. First of all, I like to thank Anshan ma'am and then GMTSAR instructors for their guidance toward this workshop. So, first we go through what I learned, the insights I got from this workshop. So, I got a basic foundational skills from for InSAR and InSAR theory, and how to acquisition the InSAR data and assess Sentinel-1 and allows data, and then how to installation and processing that, and then usual scripting also I learned here. So hands-on exercise. So I generated into programs over Los Angeles and generated S-bus time series generation over Mexicali Valley region, and also worked with the DEM creation, and also that my own study area I downloaded for time series analysis. So these are the first interprogram generation over Los Angeles. So in this, so these are two data I acquired, 12 days temporal data, 12-day temporal baseline data. So in this, wrapped interprograms and unwrapped phase intergrams, and then line of sight displacements we got. And then another is S-bus time series generation over Mexicali Valley region. In that batch processing and the time S-bus and then time series analysis, three things we did. So 5 data, Sentinel data taken as input. Here that 9 interprograms we generated. So here you're able to see that wrapped 9 interprograms and unwrapped 9 interprograms and the line of sight displacement. These are the time series analysis. Actually, output in Sabas, I got a GRD file displacement. From that, I calculated mean displacement and analyzed the mean displacement over time like that for analysis only. And then this is a problem statement and my study area. I am taken Kaveri Basin because I taken this because I have GPS data for that for 4 years data. So I want to, for validation, I taken this area. So in that area is groundwater and then lots of agricultural uses are there. So and then it's also coastal area region. So I want to take that as my study area to analyze InSAR analysis. So here I taken two images for interprogram generation for span 360 days temporal baseline data. So here I generated orbit correction, co-registration, interprogram generation, coherence, phase filtering, and phase band wrapping, and the displacement measurements. Here the rapid phase interprograms. These are for each uh, sub IW1, IW2, IW3 I generated. So unwrapped interprogram actually that is processing. So till now, so that is not there available. So my future work and analysis plans are I want to multi-temporal time series with additional applications, more than two data, and then I want to correct atmospheric corrections using Diacos, and then validate with my that field data. So long term is trend analysis and the correlate analysis with the groundwater levels, and that integrated multi-sensor different sensors I want to integrate uh, and analyze that. So, thank you.
Thank you. And let's see, usually after each talk, we have time to ask one short question. Anyone have comments or questions on her talk? And I have a follow-up comment here. So for the Los Angeles sample interferogram, so if we just plot one interferogram, we could unwrap the phase. And often the phase are not, unless it's a really large signal, a lot of those phase fringes we see are due to tropospheric noise. As you mentioned in the future work plan, we need to focus more on the tropospheric noise mitigation. So one of the methods to be able to mitigate the tropospheric noise is that typically the deformation will have some kind of, sometimes there's a long-term subsidence or seasonal feature. So they're going to have some unique characteristic depending on the deformation signal you're looking at. On the other hand, although the tropospheric noise is spatially coherent, correlated like the deformation feature, the turbulent component tends to be kind of random in time. And so instead of having just 5 acquisitions, if you could acquire a larger stack of interferogram, like run a longer time series, and then usually through fitting to this noisy data set, you're going to get a much better mitigation of the tropospheric noise. And if your area has a steep topography, and in this kind of case with stratified component, then those weather model correction also can help. So that's just a quick comment on that. So thank you.
Thank you.
Yeah, and you may unshare the screen now, and we will move to our second speaker, Stephen Brooks, and his talk is Active Faulting Dynamics and Surface Deformation at Mount Antenna from Sentinel-1 InSAR observation. Stephen.
Yep, good evening. I'm sharing my screen. I don't know if you can already see it.
Yes, we can see it. And now, right now, it's not in the presentation.
Yep, okay. It should be right now.
It looks great now.
Okay, thank you very much. Yeah, so this is pretty much my PhD research object. I just started 6 months ago, and I also started with InSAR 6 months ago. So for me, this is what actually I really appreciated about this course is the whole part of theory that was done actually pretty amazing. And also I want to thank for all the actual documentation we had on internet about the GMTSAR documentation, because I found it really useful, because you have a lot of examples and all the scripts are actually explained pretty good. And also I want to thank for this manual you guys shared about the InSAR theory and practice, because I find it very useful for who, for example, like me, is just starting with the InSAR theory. I also found pretty good the GMT plotting, because I'm new also on that. So I've been testing myself on the different plots I actually did through my analysis. So what I've been testing myself on was the P2P processing, and I used the ALOS for the example that Wei tested on the Haiti earthquake. So I actually reproduced it, and it came out actually the same. But what I wanted to use was the Sentinel-1 to test my pretty much my PhD research. So what I did is the directory building, interferogram formation, and then all the phases of phase filtering, atmospheric correction, and phase unwrapping. So as for my general workflow, I use the simple workflow. So pretty much data selection through the ASF verdicts. What I did is I tried to implement this part here. So instead of downloading the data as full safe images, since Aetna, as you can see here, falls into a little region, so I just need a few bursts. What I did is use this burst to save script. The burst to save script makes me create a small save file. So instead of working with 4 gigabytes file, I work with just 400 megabytes. So I have a smaller data set, and it's a save file with just a few bursts. So what I did next, and actually it's untested for GMTSAR yet, so I had a few issues with the time series, but it works when I use the S1 TOPS frame to generate my interferogram, and then later I use this merge and wrap geocode GSH to do merging, unwrapping, and geocode of my interferogram. So what I got in the end was the single interferograms plus loss displacement maps. What I want to present here are 3 different examples of Aetna study case, which is one of the biggest events on Aetna in the last 20, 30 years, which occurred in the Fiandaca fault, as we can see in the star in the left image, which is the general wrap interferogram. So this earthquake corresponds to actual lava flows from the central crater of Etna. In fact, we had on one side, on the left side of the volcano, we had a sort of collapse right on the collapse. Right on the right side, we have this flank instability. So what I show on the right image is this loss displacement. So what we see actually, we have around of 20 centimeters displacement on both sides of this right transtensive fault. This is a little zoom of this earthquake, and that's actually what we can see. And the same thing I did is that Etna actually has different styles of events. So this is the big one of the last 20, 30 years. But then we have even small earthquakes, as we can see here on the Pernicana fault, which is that's the northern boundary of the flank instability, of the eastern flank instability, which was a magnitude 3.7 event. And always in this case, we have a transtensive fault, but with a left lateral movement. In this case, we have very small displacement, as we can see in the zoom, were in the order of around maybe 6 or 7 centimeters. And this was connected to a seismic swarm in that same dates. And it was around February 10th of 2025, so one of the latest events on Etna. Same thing is this case here, but in this case, we're talking about a seismic creep, because what I'm studying is the relationship between the stable sliding, so creep events, with stick slip events as the ones we just showed before. So in this case, we see that we have 2 small faults that are Acicatene and Acitrezza that had this little small events around 2.53 as magnitude. And on the right, we have a little island that's called Lake Island that through GPS data, we see it's moving eastward. So in this case, if we go look at the displacement map, we can see that there's this island to the right. So these are the 3 different study cases I got in count for my presentation. So what I want to do next is obviously apply my general workflow atmospheric corrections, because actually that's what I've noticed. Actually on my interferogram, I have to apply this atmospheric and tropospheric corrections. I also want to try to implement the burst to save script to the time series, because I think it's very useful, especially if, like, for example, you want to do a 10 years time series, so that you work with a smaller data set. And then obviously through using the SBAS that we have, that you guys just put in the GMTSAR. And that's all. That's what I did during the course.
Great. Any questions?
I have a question or a comment.
Yeah.
This is Dave Sandwell. First of all, burst to safe, I'm gonna have to learn about that. It sounds great. Can you
Yeah.
give it more than one burst and have it merge the 2 into a safe file?
Yeah, exactly. What I did, if you can see, maybe I can go backwards. I'm gonna show you the ASF. Okay, so for Etna, the problem for Etna is that actually we have, if we want to generally do a simple interferogram, we need 2 save files as we can call the north part of the north save files in the south. So we actually need 4 of them. But this burst to save, what happens creates this save file, but with merging just the burst you need. So you put in a bounding box with the relative orbit, and it creates this smaller save file that actually GMTSAR, as it says, it's untested, but for single interferograms, it works pretty great. But then I had problems with the time series. It seems like when I get to the EF2, the F2 frames, it doesn't work because it has problems with orbits. So I want to try to debug this problem here.
Sure. That's great. I'll have to learn about that. That must be a Alaska satellite facility.
Yeah, it's actually a script from the ASF, and because I use it actually with ICE2. With ICE2, I did my actual time series for the same area using 10 years data from this burst to safe script, and it creates the burst to safe is the name if you want to download it from the ASF. But then if you have to do a stack, it's called burst to stack. So you put in dates, and it creates the save file with that geometry for actually all the dates you put in.
That's great. I have one more comment.
Yep.
When you showed those small offset faults, you should run that again and go into the config file and turn on the phase gradient.
Okay.
And I think you'll be surprised. You'll see those come out, but you'll see other ones as well. So try it.
Okay, so phase gradient. Okay.
Yeah, turn that on and it will run the same, and you'll get files that show the phase gradient. And
that could help out. Yep. Okay. Thank you very much.
sure, great.
Yeah, great. And our next speaker is Renan Ferreira, and the talk is Shallow Earthquake in Romania, Roraima, Brazil.
Okay, first of all, thank you for the opportunity for this presentation. My name is Renan. Let me open the video. First of all, I think was in Roraima, but actually it's close by there. It's in Guyana. But let me show it first here. I would like just to presenting. I'm Renan Ferreira, geospatial scientist with a master degree in aerospace engineer from University of Rome. Also, I made the certification of ICC from EarthScorp last year. And also I made my master thesis in the German Space Center in the Radar Institute in Munich. And also I'm leading some innovations from environmental monitoring here in Amazonia. My thesis was developing of ionospheric scintillation estimation with ILUS data, exploiting two techniques. It's Faraday rotation and autofocus. My thesis was about to take it from Aurora Borealis, that from images from Fairbanks and B waiver. So we know that the L bands and P bands, they have this problem for ionospheric scintillation due to the size of the band. So the DLR, they was trying to propose two techniques. This Faraday rotation autofocus, so I will not take too much the time from here. It's just the autofocus technique. It means that you take the left half battery and the right half battery, and you make a cross correlation, and you can get the strong scintillations. Like here, it's in the left, it's Fairbanks and the behaviors. So, and the Faraday rotation, you have the quadpole polarization. So, if you make a relation from relation from the angles for the rotation angles from Faraday rotation, so we can take these strong scintillations. This is Fairbanks was more stronger than behavior. And go to the project here. My project was to understand and use the InSAR techniques from investigate the earthquake that occurs in one geological stable region that's not so common to take a earthquake. So somehow I choose this place. I was thinking about it. Could be in Roraima, but it's not. It's this region here. Like it's old geological region. So the earthquake was more or less this region here. Oh, just a minute. Just let me. So it was this region here in Guyana. It's occurs with this Precambrian geological formation of 1.7 billion years old. So it's a part region traditionally regarded seismically inactivity. So there's no, it's not so common. This was the first time. So the rupture happening in a small privileged unrecognized fault system suggests a tension and accumulate in inspector way. So somehow this rock take a lot of pressures and from like and this rock it was at first time it's just had a rupture, so it was a strong rupture. And the InSAR process with GMTSAR, it's we can see, and it was shallow the earthquake, so it was nice to see from GMTSAR. And also I made with the ICC technique as well, just to see. But for the moment I was thinking it was I tried it with the 3 sands, but it was not possible to make the ramp due to the size and the memory of my computer. So but also in the ICC software, it was possible to see here. Was the one ramp, so we can see that in one part of it go up and the another parts go down. So it's from the papers that I search about. So there's a lot of papers about this earthquake from 2021. So the surface deformation was more or less 40 centimeters. And so I use these two techniques from GMTSAR and ICC. And for me, the GMTSAR, it was better and more precisely like the resolution, the filters. So it was better to see the shallow from this earthquake. So it was two displacements, both the vertical and horizontal movements identified. So it was possible to see the eye of the storm effect, the center of the rupture zone. Just to compare the two processing, GMT process high resolution rapidly. For me, I made this process just one day, so it's pretty interesting. Efficient for quickly analysis. For me, it was the only problem that I use Windows, so I need to made a virtual box. For me, I spend more time doing this virtual box than the analysis. And ICC, it's more modular, so an automated workflow. The only difference that I made the 3 sands with the ICC, but it was not possible to make the ramp. So, but in the GMTSAR, that the big difference that I could make this ramp process, ramp phase. And let me see, the high stress drop and 5 to 12 Pascal, megapascal. So it was significant for intraplanetary earthquake. And the displacements for a shallow earthquake, it's a clear uplift in the epicenter region. I think it's lucky. Let me see, there are other important things. And it was pretty interesting, just for conclusion, that the Guyana earthquake was a unique opportunity to study seismic activity in a tectonically stable region. So it's not was it was the first time in the region one earthquake. And these are available, provide invaluable and capturing small but significant surface displacement in a remote area. And the analysis revealed a stress buildup and rupture mechanism in a unexpected interplane region. So it was pretty nice. And that's it. If anyone have a questions.
Thank you so much. Anyone has comment? Yeah, I have one comment. And so there are many different InSAR software available. And I think that's a good thing because typically, regardless of what InSAR software you use, the wrapped interferogram you generate should have a comparable quality. And if you have noticed that there is a substantial difference between the two, and you should notify us, so we should look into that. Usually the difference would be due to a software bug or something. But beyond that, how to unwrap the phase, each software may set up differently. That might lead to different speed improvement. But overall, the interferogram should looks the same regardless of what software we use. Of course, all the software, they need to be maintained. They need bug fixes. That's why if someone noticed the difference, they should let the team know. Yeah. Thank you.
The GMT for me it was pretty nice, especially for
Yes.
the filters.
Yes, and every software, they will have additional routine, like the fact you can use GMT to create plots, and these and some of the other software already use GMT, so that probably provide better kind of interface on that. Thank you.
Okay, thank you very much, guys.
Yeah. And let's move to our next speaker. So Justin Krier.
So hello, my name is Justin Krier. I'm looking at the Lamplugh landslide. It happened in Alaska and InSAR feasibility in glacial regions. So right here, I'm starting with just a Lamplugh landslide. It's a landslide that happened in June 28th of 2016. Currently, my work looks at doing inversions using seismic and trying to understand the forces associated with a landslide. And so a lot of that is dealing with like the mass movement that happens with a landslide. And I was hoping I could use InSAR to help get a better idea of maybe some of that mass movement that is happening with the landslide. And again, just start working towards more parameters of potentially using for the inversion. So let's get into the InSAR part. Looked at this region, it was descending data, start off with correlation. You can see right here, kind of zoomed out right now, but the region I'm looking at is pretty small right here. We'll zoom in a bit, but again, this is a large area and there's a lot of not great correlation because it is such a glaciated area. And so again, just kind of get an idea looking at some of the interferograms. This is unwrapped interferogram. Again, you can see that this region, lots of noise, lots of decorrelation, and that's the region I happen to be looking at. So learning has occurred and just again was just curious as to how this would work. Originally, I wasn't sure, didn't know that there would be such a issue with the region, but that is something I learned within this course. And so again, that's something that was useful. This course of learning has occurred. Ran into issues. This one of the other things that I ran into was trying to do the geocoding and get the coordinates to fit. You can kind of see right here, I have GMT has a map of the waterways through the region, again, zoomed in to where we're at. This star is where the landslide is supposed to initiate. And you can see just based off of the InSAR image that like, it's kind of like, you can see the exact same waterway here, but it's off. I learned that I was just using the wrong files, or when you use geocoding specifically, use the wrong file to make those corrections for just one of the subswaths, because I'm only looking at one of the subswaths instead of all three that were downloaded. And so I had to just grab a different trans from a different location to be able to set that up. And eventually I got to a point where everything was fitting and we had the right locations and everything. So right here is between before and after two sets of data from Sentinel-1, and this is one that was before the landslide and after the landslide, and looking at the difference there. And so again, we can see this region zoomed in, like this little region right here is what I'm looking at, specifically where the Lamplugh landslide is. This is where the landslide initiated. and you can see that it's again just a lot of noise. And this was, I was messing around a little bit with changing, and this was the best to kind of have like the region kind of show up some of with not just being all completely noise with that limiting factor. And then so we ended up with this, and it kind of wasn't a lot to see because again the whole region, which you can see is pretty much directly north from this path, is all really noisy and hard to see anything happening. So I was curious as to what it looked like if I just looked at pre-landslide and post-landslide and see if that led to any insights, because again, just checking it out and seeing what I can use this tool for and better get to understand it. And so I just did pre-landslide and what it looked like. And again, it is a glacial path, so it still has a lot of noise. There has been smaller landslides that happened there before. So this was just a big landslide that I was recording, or a glacial slide. And so you end up with, again, there's still a lot of noise in the region that I'm looking at. And again, this is pre-landslide just to see what it looked like with 2 dates that were before the landslide. And then I did the same thing post-landslide right here, which again, you end up still with a lot of noise in the region. And so it's again, just like messing around to learn more and see if I can actually get anything to use for an inversion for this study. And again, just starting to learn a new tool and better understand it, and see if there is any way to use InSAR better for glaciated regions. And so if you have any questions, please ask them. Once again, Justin Krier, University of Oregon. And if you want to reach me, there's my email.
Thank you. Any comments, questions?
Like David.
Yeah, I have a question. What did you use for a threshold for geocoding or masking? Do you remember?
The threshold was 0.0125 was what I was using.
Okay. You can fool around with that, make it smaller, and see if you get more phase deeper into the glacier. Maybe you'd already.
That's kind of where what I was messing around with was that threshold. And this is kind of like where I ended up in a place where you saw the most without it just being like all noise.
Yeah. It's a tough area. Yeah. Thanks.
Awesome. Thank you, David.
I also have a follow-up comments here. So for this landslide, those are usually like with steep terrain. It's a pretty tough area. And in these kind of areas, sometimes when the landslide motion are getting too substantial, and it might actually lead additional decorrelation in this area. So like InSAR, like the phase really is meant to capture a minor movement, because you can think about as the fringe getting denser and denser, they start to decorrelate and lose that pattern. And in this kind of a case, typically L-band data will kind of behave a little better because they can kind of be more like tolerate a larger amount of motion. So NISAR just launched. So hopefully once you have the NISAR data, and you will see better phase quality over these kind of region.
What kind of data did you say?
L-band, basically an L-band SAR, like if you want to look at how the data looks like historically in this region, the ALOS data is an L-band sensor that kind of give you an idea for the same kind of terrain, how less, like how much noise reduction you can get from just the benefit from the fact you have a longer wavelengths, right? And we're going to soon have the nicer L-band data, so that usually will perform. Like it's still going to be challenging, but I think it's going to be easier to work with than the C-band data over this area. And also, if you're really expecting very, very large motion, so when the motion actually goes beyond like a pixel, then you can use a pixel offset tracking. And so that's usually meant to track much larger motion, like near the fault of a co-seismic region or like a very large landslide. Yeah.
Awesome. Thank you. Appreciate that.
To the next speaker. And so the next speaker is Suman Kumari. So the title is Mapping of Dike Intrusion in the Main Ethiopia Rift.
Okay. Hi, everyone. So my name is Suman and I am a PhD student. I am based out of London. So this was a great learning experience for me. because I have a background in remote sensing, but most of the time I'm working with optical data sets. So overall, I had a great experience. So I tried to generate the interferogram for this region. So this is the map of Fentele Volcanic Center, which is seismically and volcanically active part. And this is one of the most active part of main Ethiopian rift. And historically, I think there had been many events, but the last was observed in 2015. And after that, recently, the most recent was during 2024 and 25. So I managed to generate the interferogram somehow. For me, it was quite difficult because most of the I am a Windows user, so most of the time I spend most of the time on virtual environments to learn how to do that rather than analyzing that. But somehow I managed it. So I followed the instructions. So one of the references images that I have used was from 30th of October, and the secondary image was from 22nd January, I believe. Yes. So this is the interferogram that I was able to generate, but I wouldn't know that whether it was the right interferogram that I have generated. So I matched it with the recent publication. So it was similar. So I was happy that, okay, I have created something which is similar to that. For now, because I am still learning it, I don't know how to analyze it. So it was a bit difficult and part for me, but I'm still learning it. And this is the unwrapped phase, like it was said in the tutorial that I have to use the unwrapping. I have to set the unwrapping at 0.1. So I tried that, but I'm also interested in knowing that what would happen if I change it to other parameters. And the challenges that I have faced was quite a lot because for Windows, it's actually very difficult. But the one thing which I observed was the change or the loss of data. My instructor, Dunyo, he suggested that it might be due to low coherence of these areas. I did not get time to check that, but I'll surely do that to be sure. Other thing, because I was taking help from my colleagues as well, because I'm not Ubuntu user. So that while we were doing the processing, for the interferogram generation, it was using all the processing powers, but when we moved to unwrapping phase, it was only using one of the processing core, I believe, the way they mentioned it. Because so if anyone can suggest something so we can do parallel processing, that would be helpful. And that is all. Thank you.
Any comment? I have a comment. Could you turn back to the previous
Yes.
slide? And so there are probably many reasons that can cause the unwrapped interferogram looks slightly smaller. But one possibility is that your DEM didn't cover the topmost region. So that's what I was able to reproduce something similar to yours is if your DEM usually you need to be larger than your study area to preserve the whole thing. So if the DEM is actually smaller, it looks like a straight line chopped there, and it's smaller than the sentinel thing. And the phase unwrapping nodes, only the area with the DEM actually has the topography phase probably removed. And so they usually do not unwrap that region. So that can lead to like you're missing the top portion. But for this case, I actually think it is probably better, better because then the size of the image is smaller and you preserve the most of the signal you're interested in.
Okay. Okay. I'll check the DM as well. Yes. Thank you for that. Thank you.
Yeah, and another thing I can comment on is Snafu does have a switch to turn on multi-core processing. I think currently the parallel unwrapping is done in when you have a batch unwrapping, so they can launch multiple jobs. And but there's also a way to turn on the snafu. There's a switch that will allow you to do parallel processing.
Okay. Okay. Thank you.
Yeah.
So thank you very much, and I'm happy that I learned something new.
Okay.
Thank you very much.
Thank you. And our next speaker is Vaska Lokes. And his talk is GMTSAR based processing deformation analysis, processing steps, and the practical challenges.
Okay.
Yeah, but
Good morning, everyone.
if you could click the bottom, and that's probably gonna help, but you can go as it is. Some reason it
Is
doesn't.
it okay now? I think something happened with my system.
Yeah.
Is it
Maybe
okay now?
you can go ahead. We can see your slide. Yeah.
Yeah. Okay. Good morning, everyone. First of all, I would like to thank for at Scope team for giving this opportunity. This is Vaska Lokes. I am currently working as a junior research fellow at CSR National Geophysical Research Institute, Hyderabad, India. Now, I would like to present a small presentation regarding GMTSAR based post-seismic deformation analysis, processing steps, and practical challenges, which we have been working from July 14 to August 6 in this short course. I will highlight some important processing steps and errors which we face challenges in this workshop shortly. So my main goal is to analyze the ground displacement from earthquake using Sentinel-1 SAR data via GMTSAR. So while started the process, I have the two options. One is example data provided by the GMTSAR website, and the second is my interested area. In the website, they provided everything, have the interferograms and orbital files and DEM. While coming to my interested area, I have to generate the orbit files and DEM for interested area. So in subsequent sites, I will explain how I will go into the processing steps and where I got the errors and challenges. Okay, for this work, I have chosen the GMTSAR because it's open source and flexible and efficient for processing Sentinel SAR data and LOS as well. For this work, I'm using the workstation, which is compatible with the 64-bit architecture and storage capacity of 1.8 TB, and RAM is 64 GB. I think it's well suited for this work, and I will demonstrate the step by step what I have gone through and where I face the challenges. For the step one is installation. Simply just go through that GitHub, just git clone. I just installed it with that this command line. For the confirming that, I use this ERSP and face diff. I just confirmed it's working well. Next step is that I generated the working directory. For example, I'm working with that example Greece data. That's why I choose this. And for that, I created the two subfolders in raw and topo, raw as well as already have that example data that for interferograms and corresponded orbit files and a DEM file as well. The step 3 is the configuration file. Just using simple this command pop config.csh in working directory generated the configuration file. And orbit file, we have the two options. We can download from the website, and otherwise we can use this command for generating our orbit file for our interferograms correspondent. Uh, so actually, I got the started the trouble from DEM generation making. So I just gone through that website. I just gave the lat long bounds for SRTM1 DEM file, but it couldn't happen because it's saying the error is registration not done. And just up to the second option, make underscore dm.csh. So even this is also not have been worked with the help of team madam suggestion. I just verified inside that which make DEM file in bin, so which is not found. I just with the suggestion I just uninstall and again install and run this code again. It's working properly. And another challenge I faced that first my interested area is this So I choose this lat longs within this range. Maybe I missed this proper lat long, and with the suggestion with Anne ma'am, and I choose the lat longs out of this image bound, and I started again this GM generation working properly. Then next step is batch processing. For that, I just prepare the raw and topo files inside the data raw and corresponding orbit files and the DEM files. And for that, next process is the P2P processing. For that, we have to align the sequence wise. First, the image corresponded that orbit file, and second image and that orbit file and configuration file we have to arrange. And I just run it. It took almost 4 hours, but I couldn't see anything in the terminal. I just forcefully killed the process. I just contacted my batch guide and ma'am, and she's told that send that log file. After verifying this log file, it's working properly, but forcefully I killed it. I thought it's not working. It's not giving, providing any process in terminal. So again, same PTP command run. After some time, which 4 hours later, it generated F1, F2, F3, and match folders as well. In each F1 F folders, found interferograms in each F folder. I confirm that I'm able to generate the interferograms in each folders. So after the this interferogram generation, we have to do the unwrapping. So here also we faced a lot of issues for the unwrapping. So with the help of the team, I could able to unwrap the face. First of all, using first of all, I did this unwrap step in working directory for all at a time, but it couldn't happen. After that, I just uses a snafu command for each F folder. That run for each folder separately. Then those generated the interferograms. And here are the interferograms. These are the example data for Greece. We can see small fringes we can find here. Because of this ocean area, I think less correlation. We couldn't see this best signal here. After unwrap, I generated this unwrap phase, and this is for F1, F2, and F3. This is F3. I didn't generate the unwrap phase. And this is for my interested area, Mulgu event, 5.2 magnitude local earthquake. I tried for this. I choose to a pair of interferograms, and just run and generated this interferogram. Just after unwrapping, we can see here. I think I'm not much experience to analyze this. So even I'm able to generate the interferograms, and I can unwrap the things. I will learn this short course. The key achievement in this successfully generated the unwrap interferograms with the Sentinel data. I can and verified the complete InSAR workflow using GMTSAR example data and real seismic event and any region. And again, initial experience of phase unwrapping, and established repeatable and well organized process in chain, because I can able to run this GMTSAR command to generate the interferograms at any area. So currently, while the workflow flow is very functional, and certain challenges are uncertainties remains, particularly in unwrap, like which threshold I have to choose, and post mode and tile size, etc. And further, currently I'm next step is processing of time series analysis, seeking the additional clarification and guidance from team. This is from my side. Thank you.
Thank you. I have one quick comment here, is that on your page 6, I think when you're trying to unwrap, the interface quality is actually quite good. And so you probably can lower your threshold a little bit, and so that you don't end up having like all the points masked out. So that's one comment I have. And also, one of your cases is an island region where all the land area are kind of separated by the ocean. I personally have some difficulties in this kind of region, so I'm kind of curious. So if anyone else has some insight on how to deal with these kind of region. And perhaps it's just gonna be quite difficult. And David may have.
I could comment on that. So if there's water between the two areas that you're unwrapping, there's of course no phase connection, and one area will unwrap and the other area will unwrap, and they may be off by exactly 2n pi. So one's higher than the other. So one could go in there sort of manually and adjust the level of one of them to match the other. But it's, yeah, if you had GPS, you could do it, but it's always 2n pi, which is good. You know the number, so.
Yeah, so the mistake would be always a 2 pi of an integer. So if we have at least one calibration station on each of the island, then we can probably pin that a station.
Yeah,
together, right. Okay, thank you, David. And so I think after it's 10:57, so we're going to have a 3 minutes break. And then we will start right sharply at maybe 5 minutes break. And then we'll start after that and at 11:02 for Eirini Marino. Our session is back with the music, so we'll continue. And so our 7th talk is from Eirini Marino, and her talk is InSAR processing of Sentinel-1 data over Santorini using GMTSAR.
Thank you very much. So hello everyone, my name is Eirini Marino, and today I will walk you through the results of my InSAR analysis over Santorini in Greece using Sentinel-1 data processed entirely with GMTSAR. So as you all know, this presentation is part of the GMTSAR technical short course, and I will show you both the step-by-step workflow and the displacement results for the time period January to February 2015. So these slides provide geographic and geological context for the study. So starting from the left, first we see a general map of Europe showing the location of Greece inside this red rectangular dashed rectangular, showing the exact location of Greece and specifically the South Aegean region where my study area lies. In the middle, we have the geodynamic map of Greece highlighting the broader tectonic setting. My study area is Santorini Island and is part of the Hellenic volcanic arc, which is formed due to the subduction of the African plate beneath the Aegean microplate and the overall Eurasian plate. So as you can see in this map, we have these yellow GPS vectors and some fault structures indicated by the red color, indicating active crustal deformation in the whole area. On the right, we have the geological map of Santorini showing the island itself. So the caldera and all the surrounding lava flows, some faults and some units are visible. So these help the overall understanding about the volcanic structure and where the formation may concentrate in case of an event. So Santorini is one of the most active volcanic systems in the South Aegean. So why Santorini and why this specific period, January and February 2025? So Santorini was chosen due to a recent and well-documented seismic crisis that unfolded in the early 2025, as shown on this left-hand seismicity map. So this crisis began with a cluster of earthquakes, as you can see in the map, northeast of Santorini near the submarine volcano Columbo, and the island Anidros, which is not visible due to the clustering of the earthquakes. So after 24th of January 2025, this seismicity migrated offshore. So you can see the epicenters, which are color-coded by date, as you can see in the legend. And it's quite visible, this progressive migration pattern towards the north. Just to complement just to complement these findings, on the right, we have the InSAR derived displacement decomposition maps, which are for 2023 to 2024 and 2024 until 2025. So in both cases, for the vertical and the horizontal displacement, it is actually visible the vertical uplift and some horizontal displacement, which is also visible in the time series for multiple GNSS stations supporting this cumulative deformation signal. So Santorini has both scientifically and geophysical interest, make it an ideal candidate for testing InSAR technique using GMTSAR. So my study area, first I defined the exact area of interest used in the analysis. So this is the boundary box in Google Earth, and it was large enough to capture the full caldera and some surrounding area in general. I then generated a relief map and a hillside view of the dam to assess terrain variation, which is of course essential for accurate phase 2 displacement conversion during the final geocoding step. The dataset I used, so for this case study, I selected an interferometric pair of Sentinel-1 data that covers the January-February 2025 deformation period over the Santorini island. This image, which is known to everybody, is the Copernicus Open Access Hub, where I downloaded the data. So this green box shows the satellite swath covering this region. The reference acquisition is from the 12th of January and the secondary from the 5th of February. Both are in interferometric width mode, SLC products with vertical-to-vertical polarization. And I downloaded manually the respective orbits, making sure that they fit perfectly with the satellite images. Both the satellite images and the orbit files were renamed in order to be perfectly compiled with the GMTSAR in order to run smoothly. I used the P2P processing.csh for this pair of interferograms. On the left, we see the first amplitude image, which represents the radar backscatter from my reference acquisition. And it's quite useful to visually identify some landforms and coastlines. In the center, you can see the correlation or coherence map, which kind of measure how similar the radar signals are between my reference image and the secondary. So these high values indicate some stable surfaces such as buildings and mainly here rock. And on the right is my wrapped interferometric phase. And this is where the deformation begins to appear, particularly visible around the caldera. So all these were used in the next steps, in which you can see the raw wrapped phase after the interferogram generation. It's mostly dominated by noise through deformation around the Santorini caldera is already visible. In the middle, the interferogram has been filtered using a spatial filter to reduce noise and improve phase continuity. So on the right, there are not quite visible differences, but there are some very important. Is a mask derived from coherence and has been applied to exclude low quality areas in my study area. This is just a screenshot I really liked from Google Earth, and it shows in a 3D formation Santorini, so I really like this one, so I added it. And here is my final output. On the left, we see the unwrapped phase in radar geometry. And moving in the final and my final results, it's the geocoded line of sight in millimeters, which is overlaid on geographic coordinates this time. So this is the interpretable result showing deformation centered around the volcanic system between January and February 2025. just to zoom in a bit, because it's quite interesting for me, this I would like to highlight the deformation pattern in more details. So this concentrated uplift in the southern part of the caldera suggests some pressure accumulation at depth, likely related to magma intrusion, possibly, aligning with what was observed during some previous unrest period in this area. So the bright red yellow ring in the center of the caldera shows some uplift, so some positive line of sight displacement. This could be caused by magmatic pressurization beneath the volcano, while the blue purplish fringes surrounding that area may indicate subsidence or some lateral deformation. Whatever is green colored, it remains neutral, and we have no substantial deformation. These black areas, yesterday, Kang told me how to enhance these areas with the filtering option of Snapu. So this is one of my next goals, to improve this image as much as I can. Lastly, some reflections and challenges for me. So what worked well? So one of the greatest strengths of using GMTSAR is that it gave me full control of each processing step. So from raw CLCs to displacement map, I really enjoyed it. I managed to integrate these satellite images into a seamless interferogram. So this modular nature of GMTSAR allowed me to adapt, even when the some expected scripts that I found were probably missing. So I could still find several alternatives. I also highly appreciated the strong community support, especially via GitHub or the GMTSAR documentation site. So overall, it was a really valuable experience, both in InSAR theory with the plenary sessions and the Unix-based practical skills. So some challenges, while the community and documentation support is excellent, is kind of split across different kind of places. So from the official side to GitHub, so it's not always consistent, even though it's a lot. The GMT syntax can be tricky, but it's quite challenging at the same time. I had issues with this P2P processing, but I managed to solve it manually, and it's working perfectly. And lessons learned. The GMTSAR favors flexibility definitely over automation, which, understanding the theory, it really matters. You can build your own processing workflow, and helps you learn every step of the InSAR processing workflow. It is important, at least for me, to always verify the output step by step before moving forward. It helped me a lot. And I can definitely tell that modular tools like GMT and Snapu are quite powerful, but they require careful tuning. And it, of course, demands patience, but the result at the end is quite beautiful. Future work, I don't want to stay long here. My ultimate goal is to explore the final integration with some Python-based tools, and create my own semi-automated pipeline for this GMTSAR processing workflows. Thank you very much for your attention, and I'm happy to answer if you have any questions.
So I have a question or a comment. First of all, that was a great presentation, and I understand how the learning curve on all of this is really steep. But once you get up there, it's not so bad. But I do have a comment on the processing. It looked like maybe the DEM you used didn't completely cover the SLC area, which is fine because you were just focusing on the center part. But there's a thing in the config file called SLC cut, and you could tell the processing, I just want to focus on this small area. You have to do it in range and azimuth coordinates, but then it would save a lot of time and make things run faster. So, but otherwise, great. Yeah.
Excellent. I'm taking my notes right now. Great. Thank you very much.
You have to look at a PDF of the range in azimuth of like the amplitude image or one of those, and to get the range of ranges and azimuths that you want to cut on. So, yeah.
Thank you
Great.
very much.
And we will move to our next speaker and Payman Nanda Sahat. So sorry about that. And so are you here? So maybe we will skip to the next one and come back if the student are joining. So our next speaker will be Rodrigo Pamo. And
hello, good morning.
hello, yeah, we can hear you. You may share your screen and your presentation. His presentation is the InSAR application for detection of landslide in Bamba, Peru.
Okay, good morning, everyone. My name is Rodrigo, and today I will present InSAR application for the detection landslide in Huancabamba, Peru. Okay, Huancabamba, it's located in South America. It's in north of Peru. And in this place, we have landslides, and the origin is the topography. Okay. The Geophysical Institute of Peru identify these active landslides here in Huancabamba, and we can see that in yellow areas. The yellow areas are the active landslides, and also they measure with GPS some points to check the vector displacement. So the idea is to make interferograms in this area and try to check or identify some landslides using SAR or GMTSAR. Okay, for this project, I use ascending and descending orbits. And in these slides are my images. I used images from July 28 to August 29, 1 year. And the idea is to compare ascending and descending interferograms. It tried to identify where it's located. So I will present my RAP phase interferograms. My first interferograms are from July to September 28. So in this area, I can see like the correlation in the middle of this area. And I can see this pattern in both in ascending and descending orbits. I suppose it's the deformation in these areas. This pattern occurs in every interferogram. For example, to the next, from October to December 28, I have also the correlation near to Cruz Grande, Tierra Amarilla, for example, Chontapampa, Tierra Negra. In these places, we have the correlation, and it matches with the active landslides that were identifying in other works, in other projects. Okay, the next time is January to April 29, and also I try to identify the landslide. This is for ascending and descending orbits, and it's the same. And like in Tierra Amarilla, Cruz Grande, for example, we have the same pixels, the same patterns. The next, for example, to May to August, from May to August in 2019. For ascending and descending, I have also these wrapped phase interferograms. And the last one is to identify an earthquake. Actually, in 2019, in 26 May 2019, and there was a big earthquake that occurred in Peru, 122 kilometers of depth. And I tried to make this interferogram to check if there is any deformation or if this earthquake produce more deformation in this area. And I can see maybe near to Tierra Negra, like this. I have deformation. I try to unwrap the face, but I realized that it's better if I use the wrap face because maybe there are problems when I unwrap that face. And that's all. Thank you very much for your attention.
David, I see you are up. Do you
Yeah.
want to comment on something?
Sure. Sort of the same, nice presentation, same comment as last time. You could do that SLC cut to really zoom in on, it's a pretty small area that you're looking at. And then there are some parameters in the config file that would do less filtering, like it might be set to 200 meters wavelength, but you could set it to maybe 120. And then you could, there's some decimation factors that you could change from 4 and 8 to maybe 2 and 4 to get twice as many pixels. But yeah, if you did the SLC cut, you could do all that and it would still run pretty fast. But it's nice, yeah.
Yeah, David, we should probably add a small, like a comment on the documentation for how to cut a smaller area, as is a common issue that arises a lot.
Yeah.
Right, and I think the issue is like if you have a large image, the face unwrapping gonna take a long time. But if you could zoom into a smaller area for a landslide, you usually need a higher resolution, and then you can take a fewer looks. That's from the range and azimuth looks that David just mentioned, and then so you could maintain a higher resolution while the overall image size is still workable. Because snafu does get substantially slower if you have a very large image size.
One other comment on the earthquake, because the earthquake is so deep, 120 kilometers, the deformation might be 300 kilometers or 400 kilometers across. So you'd have to look at the whole scene or maybe several scenes it's going to be very wide. But also maybe the deformation is not very big. You'd have to look at a model and see how much you expect.
Okay, thank you for your opinions and for your attention. Thank you.
Nice.
Yeah, and I think also after we have the face unwrapping, you could see this line of sight map unwrap the face. It's also good to go back to the original wrapped face to kind of make sure the unwrapping kind of is feasible in this area. So if area has a high decorrelation, then sometimes you will get a almost reasonable looking unwrapping result, but it's not necessarily reflect that wrapped face result. So sometimes it's good to kind of look at result from multiple stage, make sure they're consistent, because sometimes the face unwrapping result can be tricky in this mountainous region. Our next speaker, and we're gonna move to our next speaker, Michele Proietto, and the talk is multi-track batch InSAR processing over northern Italy, detecting transient signal related to the 2021 to 2022 drought.
So hi to everyone. My name is Michele Proietto, and I am a PhD student at the University of Bologna in collaboration with the INGV, the National Institute of Geophysics and Volcanology. And I am finishing my first year of PhD while the most of the years was dedicated to processing InSAR data over the northern Italy. And in order to give a bit of scientific context, the general goal of my PhD is to detect the transient signals associated to the 2021-2022 droughts that happened, very severe droughts that happened over northern Italy. Other studies already show, mainly with GNSS, that this transient signal can be catch with geodetic methods. The approach will involve to download multiple Sentinel-1 tracks in form of CLC images and to build a time series from late 2015 to the mid of 2024. And the final goal is to model these transient signals in the elastic load assumption in order to obtain an estimate of the terrestrial water storage at much finer scale respect the GNSS. So my area of study is the northern Italy, that is shown here geographically. What can be noticed here is that the area is quite big, so it's needed to process several tracks that are 3 for descending and 3 for the ascending that cover all the areas, and also involves multi-frames other than multi-tracks, because also in the north-south is very big. And for the moment, I already processed only the red and the blue tracks, both on the ascending and the descending orbits. So I will show a bit of the result regarding these 4 tracks. Here I show the processing workflow that I followed. I created my Python scripts in order to automate as soon as possible all the processing, InSAR processing, calling the CSH script of GMTSAR. And I will not explain each steps because as widely covered in the theoretical sessions, but I will talk about only some steps, the steps that I changed a bit respect to the theoretical workflow. The first thing is the reference point, because I choose also to reference spatially the solution. To be specific, I've been spatially referenced to the GNSS station that are available in the DOMS. The GNSS station is chosen in order to be in a point that has so much coherence as possible. At the same time, the GNSS station should be in a stable zones, so the time series of the GNSS station should be as flat as possible and should also cover as many InSAR data as possible. And then in my configuration files, my workflow, you set the name of the station, so the codes will transform from longitude, latitude to radar coordinates, and for each interferograms in parallel will be subtracted the corresponding phase value on all the interferogram. So also I calibrate the InSAR solution using the GNSS displacement. Then I also calibrate with the velocity, because I saw that in some tracks this velocity calibration was needed because the velocity solution was quite far respect to the GNSS. Here in the validation, I simply put in comparison the InSAR solution with the GNSS station available. And I also compute some very simple indexes, like for example, the RMSA and the correlation. And for the velocity, I performed a difference analysis. And then here I correct the solution because once you spatially reference to a point, a GNSS station, if the point is really stable, you don't need to do nothing. But since it doesn't exist, I think, a really stable point, I add back the deformation of the GNSS station to the InSAR, resampling, low-pass filtering the GNSS. And then I save the products and the chain is ended. Here I show the bus network only of 2 tracks, one ascending and one descending. Here is to show that as we will see later, the zone is characterized by very low coherence. So I try to put as parameter 60 days in order to have a very small temporal baseline and 150 meters as perpendicular baselines. However, the problem is like that the bus network will be disconnected, I noticed. So I added also the annual interferograms in order to make the bus network continuous. Here I show the average coherence only for an ascending and for a descending tracks. And here we can notice that the average coherence is quite low in the zones for the intrinsic scattering nature of the zones, because we have a big mountain chain that is the Alps on the north, and you have a little here chain that is the Apennines, and here there is a lot of countryside with a lot of field of crops that decrease the coherence. And here the height zones of coherence are all the cities that are in the river. The same things you can be noticed also in the descending datasets. Here I show some example, 2 examples of my thousands of interferograms. And to unwrap, I applied to this interferogram a threshold mask of 0.2. I choose these values after several attempts of solution, because I ran a lot of solution on a specific track in order to find at least the best solutions in comparison to GNSS, and then I use these parameters across all the other tracks. And this was giving the best solution, and we can see that there is a lot of faults because it's due to the low coherence in the zones. And also I masked the C that in this portion. What is interesting to notice is interferogram is these features that probably is an unwrapping error, I think, here. And I notice, especially in these tracks, that there are a lot of unwrapping errors, and especially are along the coast. I try to enable the nearest neighbor interpolation, but this error still remains. So here I will show a bit of comparison with the GNSS for all the 4 tracks, and I choose to show the best time series and the worst one for each tracks. Here we have the first 2 plots are for this track. This is a solution for the ascending tracks. This is the first tracks. Here are the second tracks. And here we have the first column is the best solution, and the second column is the worst solution. And here I show 2 solutions. One that is calibrated with both velocity and displacement GNSS, and this is the blue one, while the green one is calibrated only with the displacement. And here I show 2 indexes that are the RMSA and the correlation that are showed only for the blue solution, because in this case, both of the indexes are calculated on the detrended time series, so will not make any difference. So Starting from the first one here, we can say that the agreement is very good, in my opinion. It's able very good to capture also the seasonal component. Also, the RMSA is very low, 5 millimeters. So it's quite good agreement. Also, the correlation that is a middle correlation in reality, but at least in my opinion, is quite good agreement. While here on the other side, the agreement is not very good, I can say, especially from July 2018, from here, where it looks that the amplitude of the seasonal started to increase. I don't know, to be honest, why it started to increase from a certain point. While moving on the other tracks, you can see also here the agreement is quite good, even if there is this artifact here that is common on every time series. Not every time series, because I didn't look every time series, but at least in the 100 time series comparison with the 100 GNSS station, I noticed this particular artifacts that also is present also here. And also here we have seasonality that is not registered by the GNSS. And also here in the end, there is this strange behavior in the end. Moving on the descending, the plot, the philosophy of the plot is the same. And what I can say here, that also in this case, there is this seasonality that is strange maybe behavior. And also here in these tracks, we have these very big artifacts here. Here, and in some points are 50 millimeters. That is very a lot. And what I want to show here is that, for example, for these tracks, especially in this time series, the velocity calibration helped a lot. Because in some tracks like that, the velocity calibration helped a lot, while in other tracks, like this one, doesn't change so much. Here we'll pass to the velocity comparison with GNSS. Here I show the velocity difference analysis on the Hossein dataset. This is the histogram of the velocity differences. And here I calculate the mean and deviation standard with and without the outliers. And what can be said that at least the mean of the differences is 0.20. That's a very good results. And also the deviation standard, at least looking at the lecture tool, is in line. Here I'm showing the solutions that is calibrated both with the displacement and with the velocity, especially the velocity. Moving on the descending, we can say the same here is quite good. Here for these tracks, the mean is 0.1, is a bit worse, but is still in line with the lecture tool. And also to investigate if there is some spatial, in the spatial, there is some points where the disagreement is greater with the GNSS. I traced these wide velocity profiles, where here in the first rows, I show the localization of these 4 profiles. And here I show the seamless merged solution between these 2 tracks. And here we can see clearly this line that represents the boundary between these 2 solutions that tend to disappear going toward the south, but here in the Alps is quite evident here, unfortunately. And then here I trace the profile where this is the localization of the GNSS station. In the second row, I show with the dot point the value of the GNSS velocity projected in loss. The green points or all the InSAR points, the solution inside this polygon. And here in the blue and green, I show the median and the smoothed median in green. And here in the last row is the altitude plots along the profile. So looking at the first graph, you can see that in the beginning of the profile, there is a disagreement with the GNSS. The GNSS point a more positive velocity, tend more, whereas the InSAR tend to be more in the negative sides, but then tend to be more in agreement. And here can be noticed here that there is a jump here in the velocity, a bit of jump here. And this point is exactly where it begins the other solution, and one track solution begins the other. Here, we can say that the agreement is a bit better. And here, unfortunately, was not the best profile because here we don't have any GNSS stations, but here we have a good agreement, and also here. So apart this portion is quite good in agreement velocity. Going to the descending with the same identical plot, here, in my opinion, we have a bit worse velocity solution because here the seamless merge is, the boundary is so much more evident respect to before. And also there is this like east-west pattern here of the velocity. That the problem is some atmospheric artifacts, probably. Apart this, going to the profile, we can say also here, the beginning, there is a problem here, problem. But in the rest of the profiles are quite good agreement. Here there is a very huge, as I can say, interval of velocity with the SAR, because start from 0 in that arrives plus minus 6. But it's due to these zones that is a very localized zone of height subsidence here. And that's all. Thanks for the attention.
I have a question or comment. First of all, that was great, and it represents a lot of work. We do this kind of thing in California, and it's you have tracks and
yes, I know. Yes, the paper. Yes,
a lot of interferograms, and it's so challenging because the coherence is not very
yes.
in the Mojave Desert where the coherence is really high, but you've got like one of the toughest places.
Yes.
So I could talk to you forever about how you do this, but one thing in the phase unwrapping, you said along the coastline you were getting errors. Did you have this thing called near interp turned on in the config file?
Yes, I enabled. Yes,
Okay.
it was enabled. Yes,
Right.
I tried both to enable and to switch off, but I didn't find, unfortunately, so much big difference. And it was very, and this tracks was very so much affected by these unwrapping errors. In fact, in the solution, in the real final solution, I will cut probably these portions because also with the GNSS comparison here in these zones was completely different respect to GNSS. So it is a very challenging year, yes.
Yeah. And one other quick question. Your main objective is to learn about the uplift of the mountains due to a drought and an elastic rebound. Is that right?
Yes, exactly. At the end, yes.
Okay.
At the end.
That's really challenging. Yeah, that's yeah. Thanks.
Okay, thank you. Can I ask a question to you, David, if about very, very fast question? I don't know, in your opinion, these artifacts, because these artifacts especially are something that is something related to the atmospheric components that was not really well corrected.
It could be. Did you use the SS with the atmosphere turned on?
Yes, with one iteration. With a tuning, I found that at least for my zones, it was the best to use only one iteration.
Okay. I mean, another possible reason for that would be a phase unwrapping error of 2 pi for the whole.
Okay.
2n pi, so the whole thing is just off by a constant. But I don't know.
Okay.
There's so many possibilities.
Yes.
This area is so
Yes.
difficult, so yeah.
Okay. Thank you very much.
I can add two ways maybe you can try to troubleshoot the issue. Of course, there are many ways you can get this kind of error, and typically my experience is if it doesn't agree with GPS, typically it's InSAR, probably there's some error there because GPS typically the line of sight have a few millimeter of accuracy reliably, unless that station has some issue, but I think the station looks fine. So for those sudden jump, those large jump, and those are a pretty large error, and typically those are related with probably phase unwrapping error, but the way to be able to spot the phase unwrapping error is that you can see that day has a very large jump. So what I would suggest you is to grab a few interferogram that was formed using that day, looking at the wrapped phase and then also the unwrapped result for a few interferogram. And then you can do a cross control of the other interferogram, other day that doesn't seem to have this issue, and then the sample interferogram, because those phase unwrapping error typically are pretty noticeable because it just looks like a weird patch that doesn't have a regular boundary, and their difference is like a sudden phase jump of 2 pi times an integer. So these can be just identified by your eyes if you already know there's a particular day that has a very large jump. And also, another thing you could kind of suspect is you could see, compare the location where you have a good fit versus the location of the station where you don't have a GPS fit. So typically the tropospheric noise will increase as long as, because it's only the difference between the noise at a reference station and a non-reference station matter. So if you find all the bad fit is are at the GPS location where it's further away from your reference location, and there's a kind of an increasing kind of a divergence of the two, they're very likely to due to tropospheric noise.
Okay.
So you kind of have to see the misfit pattern. If they're kind of evenly distributed, then there may be some other issue. But then the idea is to identify not only, oh, those GPS fits better, this doesn't fit better. Look at their misfit to say, oh, this cluster fits well, and this cluster doesn't fit well. And then think about the distance where you're having the reference location, and also you could go to the actual interferogram. So what I personally find beneficial is to actually look at your data, and then you can kind of see, oh, that area really has maybe a large phase fringes due to topography, and that's usually stratified noise. So kind of identify where those misfit located, and then based on that location, their characteristics, then you could go to different kind of InSAR phase noise to troubleshoot the issue.
Okay, I will try. Thank you.
Yeah. So we'll move to our next presentation from Rajesh Silwal, and this, I think, presentation cover a different topic about ionosphere. So configuration parameter for ionosphere correction in ALOS2 GMTSAR data.
So, hello everyone, my name is Rajesh Silwal. I'm a first year PhD student here at University of Houston. And for this course, I prepared a presentation on ionospheric correction for ALOS2 GMTSAR. And the title of my presentation is Tuning Configuration Parameter for Ionospheric Correction in ALOS2 GMTSAR GRD trained versus split spectrum using GMTSAR. So before starting this presentation, I would like to thank David and Molly for their guidance. So yeah, let's get started. So I've chosen Nepal as my study area. There was a huge earthquake in Nepal in 2015, and I've generated interferogram for that earthquake. And for interferogram generation, I've used two ALOS2 GMTSAR images, one before the earthquake and one after the earthquake. And in GMTSAR, I've used P2P ALOS2 GMTSAR scanframe.css script for processing the SAR data. And from that processing, I got this interferogram that you can see here. And in this interferogram, there are like fringes that are caused by the earthquake deformation, along with the phase ramp caused by the ionospheric effects. So it is necessary to like remove these phase ramps caused by the ionospheric effect from these interferogram to get the accurate deformation caused by the earthquake, especially in case of like LS2, since it is an L-band radar and which is highly sensitive to ionospheric effect. So there are like different methods to remove the phase ramps caused by the ionospheric effect, and one of them is split spectrum that is also integrated in GMTSAR, and other is like fitting a trained surface. So in this presentation, I'll be like comparing the result between these two. Yeah, so first let's go through split spectrum technique. So let's talk about how it works first. So it basically splits the radar signal into high and low frequency subband, and then isolates the ionospheric phase by comparing the subband phase differences. So here you can see the 3 interferograms that I generated using P2P processing. And we know that for P2P processing, there is a config file in GMTSAR, and that config file has different parameter for ionospheric correction. So these are those parameter for doing the ionospheric correction in those config file. And for the first interferogram here, I've used the default config file without changing anything. So because of that, there is no ionospheric correction. You can see the phase ramps. All right. And for the second interferogram, I've changed the value of correct INO from 0 to 1 here by doing, so it did the ionospheric phase correction, but still like there are some low frequency phase ramp present in the interferogram. And for the third interferogram, I've changed the value of this DSAM from 1 to 5, which removes the low frequency phase ramp. And this is the final result I got using the split spectrum technique in GMTSAR. So next method that I've used was GRD trained using GMT. So basically it fits the polynomial trained surface to model the large scale ionospheric phase variation. So this is the code that I've used. And here the unwrapped.grd is the unwrapped phase that I got from P2P processing, and here n determines the degree of polynomial trained surface. So higher the degree, more complex the trained surface is, and this is the output unwrapped deramped phase. And I got this interferogram. Again, I used the GRD math tool to wrap the unwrapped output again to get those get these interferogram here. So, and also, so I have changed the value of n to see what it does to the phase ramp. So first I like put the value of n as 3. So there is like still a phase ramp here. Then after I put the value of n as 5, there is still some low frequency phase ramps. And again, I put n as a 6. So the phase ramp is somewhat removed in this case. So the only downside of this technique is that it removes the phase ramp caused by the ionospheric effect, but it may also like remove the phase signal caused by the deformation, which are like important for us. So yeah. And the conclusion of this comparison is that from this like comparison, I concluded that GRD trained may also like remove or distort real geophysical deformation signal, and also long wavelength ionospheric ramp or residual train may remain after split spectrum correlation. But overall, split spectrum performs better for removing the ionospheric effect. So, and you can see the visual comparison between the result of final result between the split spectrum and GRD train. So I think split spectrum looks a lot better than GRD train. So now let's talk about the future work. So I got this LOS displacement after the ionospheric correction, right? So, and for the future work, I want to like correlate the LOS displacement and normalize channel steepness index within the Himalayan region and the earthquake in this landslide within this region, and maybe like create a landslide hazard map, including all these factors, so that there is like less disaster in the future earthquakes related to the landslide earthquake in this landslide at least. I think with this, I'm done with my presentation. And also, so this is my contact information. So I'm open for collaboration in InSAR research. So feel free to like reach out to me. And yeah, thank you for listening.
This is great. And so Yeah, this is really great. So have you tried to run the ionosphere correction on other interferograms?
No, so I've only tried running the ionospheric for that particular event. I'm
Yeah,
not
so it is, I'm curious because sometimes you see ramps and some of them are from troposphere and some from the ionosphere. So the that band, because tropospheric noise does not have this dependency on the frequency. So that's maybe
Yeah,
a way to kind of identify which ramps are from the ionosphere and which one is from the troposphere. Yeah.
I can try that next. Yeah, sure.
Yeah.
Yeah, I saw this presentation before, so it's really nice job. Just a comment, this is really hard to do with ALOS data because there's not much bandwidth to the radar chirp. And so you don't have, like GPS, you have a very wide bandwidth between L1 and L2, and you can make the ionosphere correction. But it's really hard with ALOS 2, and so it doesn't always work. But the good news is that InSAR that was just launched last week will have a very wide band and do a much more accurate ionosphere correction. Yeah, again, this worked pretty well. So
Yeah, and
Yeah,
definitely.
I'm excited for that NISAR data. So
Yeah, for
it's-
NISA, we definitely have to worry about this because they're gonna have these artifacts if not corrected as well. So, but the mission is designed to work better for mitigating this issue. So we have one more talk, then we're gonna take a break. So our next talk is from Margarita Solares-Colón, and the talk is Insight from InSAR Unwrapping the 2020 magnitude 7 Samos earthquake. Margarita, are you here?
Okay, do you see the
Yeah, we see only
non-presenter?
the screen, not your.
Okay,
Yeah.
perfect. Okay. So hi, my name is Margarita. You can call me Mara for shorter. I'm a PhD student at the University of Oregon, and I'll share here my journey with the Samos earthquake and trying to figure out InSAR during this short course. So thank you, Earthscope, all of the organizers and people involved, and Catherine Guns, who was my instructor and answered all my questions and was very helpful. So why this earthquake? First of all, I wanted a little bit of a challenge, but not too much because I don't have a lot of experience with processing InSAR. And this earthquake is a large one, it's a magnitude 7. We should be able to see something. It's a little bit offshore, which is not ideal, but still I wanted to see in a good magnitude scenario, what will be the results. And also when I was looking at the seismicity nearby, there was no like major foreshock, so it should be an interference in the InSAR scene. So that's why I selected this event. And I followed the example that was on the website and GMT documentation. I used the ASF database to download my scene. There was a couple of options, but I ended up using one that I didn't have to stitch like any scenes or something just because of time constraints. And I followed the P2P processing script where I got my coherence and my filter interferogram results. Also, the event was on October 30, so it's covered in the time of the acquisition of the InSAR data, which is good. It's a descending scene and it's a Sentinel-1 data. So this is my journey in the unwrapping interferogram part. I changed later on to a wavelength of 400. This is the Samos Island, and this is the earthquake. When we moved to the unwrap phase, here I did a oh my god, rectangle to try to focus a little bit on the area that we were interested and try to change the threshold to see what we'll do when I unwrap the scene. And then I noticed that I started to lose data or points or pixels, and I was a little bit confused. So I stayed with the 0.1. And then Catherine pointed out that that could also be because of the noise that you see in this plot. And I don't know why it's going up, sorry. So I don't know, it was interesting to like just play around and try to change some of the settings. And then finally, I went to my line of sight deformation plot, where I was somewhat excited because I can see something here and something here that is indicative of uplift at subtended signal. And given that this is a normal fault event, it kind of fits with the observations. And here's just like, if you're interested, here is a focal mechanism that explains that it's a normal fault dipping north. And then I also compared to other studies to just sanity check in some sense. And although the convention is inverse, we can kind of see that I managed to acquire something that looks similar, where this will be the subsidence and then this will be the uplift. And I also read in some other papers that they actually went into the field and recovered measurements that do say that there is like a uplift subsidence from west to east in the island, so it kind of fits nicely. So I was excited about that. And yeah, so thank you. It's not a very complicated project, but I believe it was a great adventure. And thank you so much for all the GMT documentation. Ultimately, I work with slip models and large earthquakes. So if you have any suggestions about how to make like a tractable number of pixels to put into the inversion, how to focus in the area of deformation that I want to focus, how to deal with island offshore events, etc.
That was great. Thank you. You must be excited about the earthquake that occurred last week because it's a magnitude 8.8 or 8.7. And actually the InSAR there is really good. You should look at the Sentinel-1 data and also the ALOS-2 data. But it's a huge area. That's
Yeah, but there's a lot of activity, so I wasn't like sure how if we could like even see the deformation of the 8.8, which is very exciting, and I would have chosen if it was a little bit before I started working on this one.
Yeah, I mean, a lot of people will be working on it, but it would be sort of fun.
Yeah.
So I have one comment for everybody about coherence, because there seems to be a confusion about what level of coherence to use for masking. And I found this paper by Lodi. I could send you the reference. Let me share my screen real quick. I just have one slide. And
Yeah.
it's this is what they did is they compared the coherence between ice, and they call it Arasis, but it's really inside is GMTSAR, and also GMTSAR and SNAP. And so one thing they found is that typically ice coherence is higher than the other two, SNAP and GMTSAR. And if you look at these plots, here's an example here down at the bottom. This is a comparison between GMTSAR and ice, and you'd expect a 1-to-1 line here, but the ice never goes below 0.2, which is really interesting. And we've been looking more into this. But if you compare the SNAP, and the GMTSAR, they really fall in the same line, and you can get much lower coherence. So when people process data with ice, they typically use 0.2 as a threshold, but when you use GMTSAR, you have to use maybe 0.1. And it's due to a difference in the way the coherence is made. So anyway.
Yeah, and I can add to that, David. And so the coherence is actually a biased data-driven approach. So to calculate that, and so I think maybe depending on the software, they might use a slightly different averaging window. So depending on that particular recipe they use to calculate the coherence, the same interferogram might have a different value of coherence. Doesn't mean the interferogram is worse. It's just you have to experiment it, and by eyes, if you see that interferogram has good phase, and then it got masked out, you could usually push down. And in some cases, I can push down to even 0.1 or even less than that, and still don't.
Yeah, we compared the interferograms, and they're identical to within a fraction of a radian. But it's this coherence thing, and actually deep inside of ROIPAC, there's a little piece of code that says remove a trend in the phase in a 3x3 window before you compute the coherence. So they've removed some kind of plane, and it's something that was done maybe 20 years ago, but I think it accounts for this difference. But so just keep in mind that you can go lower threshold with GMTSAR than you can with RIPAC or ICE.
Yeah, that's why I usually don't use a single threshold, just memorize it for each case. It's a good idea to try different threshold and to see how many are thrown out. And if your eyes find like that looks good enough to me, then no decorrelation, then not enough decorrelation to throw out, then you can accept that threshold. And every single case, I play with that number a little bit because it's the same in the ferrogram. It's just a slightly different quality measure.
Great. Thank you for the comments. I unchair because I couldn't see the faces. Where is this paper exactly? I'm sorry, I kind of missed that trying to.
I'll send it. I don't know if I can
yeah.
put it in chat,
Okay.
but I can send it. Send me an email, whoever, I don't know. I can put it in this discourse, right? I'll put it in the discourse.
Yeah.
Okay.
Yeah, and we will take I think it's at 12:11 p.m. at my time, so we'll take a 4 minutes break and we'll be back at 12:15 for the last session, final session of our presentation with the 4 talks. Thank you, everyone. 4 minutes break. We're back for our final session in today's plenary session. So our next speaker, Alireza, Taheri, Dehkordi. So the talk is about land subsidence monitoring using time series InSAR analysis of 8-year Sentinel-1 data, terrain array.
Okay, thank you very much. Do you hear me?
Yes.
Okay, so I will share my screen. Okay, that's it. Thank you very much for this nice course and nice instructors that we had during this course. I will talk about land subsidence monitoring using time series of InSAR data in Tehran, Iran, the capital of Iran, which has severe problems in let's say supplying water for agriculture and drinking water, and they are using and over exploiting groundwater for that. I'm doing my first year in Lund University as a PhD, and my project is mostly about monitoring groundwater level using a combination of InSAR and AI models. I selected an ascending image with pass and frame number of 28 and 112 over Tehran. I processed all the 3 subswats in order to just generate a very large image capturing the whole region. And for that, I selected to process images from 2017 until the end of 2024. With that, we had 239 images available for our processes. I created a reference, actually a network interprogram of with 48 days with a spatial baseline of 250 meters, and I selected the middle image with a spatial and temporal baseline as the reference image in order to do the co-registration. And finally, I had 468 interprograms, and I did the interprogram formation using range and azimuth decimation of 20 and 5, which gives a spatial resolution of around 100 meters. And as the instructor said during the course, it's better to just consider the filter wavelength as the 4 times of the spatial resolution. So I consider the filter wavelength as the 400 meters. I did the merging and all the pre-processing needed for just doing the space analysis, and this is the final correlation of one image in the winter actually, and even you can see that we still have a very decorrelated areas, especially in the northern part because of the forest region, and also the croplands and the cultivation areas exist in the region. actually, I did the unwrapping using two different thresholds for the snafu.csh. The first one I selected 0.05, and the second one as the 0.1. And also one thing that I did notice was that most other softwares, maybe they are using, let's say, reference area as the 0 point in order to just anchor the unwrapping the interferograms to the ground. So I selected a reference latitude and longitude which is far from the subsidence zone, and also had relatively a stable deformation, and I consider a neighborhood of 3 by 3 to anchor the results to the ground. And this is the final time series map that I generated using SPAS, and I set the smoothing factor to 5 and the atmospheric factor to 3 iterations in order to get the final map. As you can see, around Tehran and around Karaj, which are very two big cities, maybe around 20 million people live in these two regions. We are having severe subsidence there, but I didn't have any GNSS data in order to compare my results, so I decided to compare it with a recent study done by Hakshenas in 2024, which they have which they have produced their InSAR maps for 2014 until 2020. And as you can see, both maps are quite similar actually in terms of subsidence zones, but the numbers are a little bit different, which is, I think, mostly about the different time period that they have used. And also, I processed exactly the same data with MintPy in order to compare and see the performance of both packages actually at the same time. And as you can see, they are producing very, very similar outputs, both MintPy and GMTSAR, the zones, and also the minimum and maximum velocity of the subsidence is quite similar in both packages. Also, I did an analysis for the InSAR for the time series actually of 2 random points, and as you can see, both of them are quite similar in terms of the time series inversion as well, and the R squares are quite high when you compare these two. So during my processes, I would really appreciate David or Jingi if they can answer me. I had 2 parameters. Actually, there is 2 parameters in SNAFU. I think David now could somehow just mention it in the paper he showed about TH1 and TH2. Actually, I have no idea what TH2 does exactly, but TH1 is quite different to the other packages that I'm using. So for MintPy and LeakSpace, usually we set them as 0.7. But in GMTSAR, even if I set it to 0.05, I would not get a very continuous map, and still gaps exist. And also, how much is it is important to just reference your unwrapped interferograms to a 0 reference point, because as I mentioned earlier, I see other packages use a reference latitude and longitude exactly during the process, but GMTSAR doesn't do that. And also, is parallel processing available for all stages of interferogram formation, unwrapping, and space analysis in the GMTSAR?
Great, those are nice results, and those are great questions, and Anne could help out with number 2 more. But number 1, this thing about the threshold, it's a little confusing because the threshold for the snafu actually doesn't do anything. If you look carefully in the code, snafu unwraps everywhere, and then at the very end it says if the coherence is below this threshold, just don't show it in the plot. So it doesn't affect the unwrapping. But the second threshold is for the geocode, and that sort of does the same thing. It'll just make the plot look different if you have a different threshold. But I guess that mask gets applied also to the SPAS before the SPAS. And number 2, the reference point, you can take 1 point. What we typically do is we reference the whole image to whatever GPS points you have in the region. So you can you can take an interferogram spanning 2 times, and you can then go into the GPS database and get the deformation difference between those 2 times and force the interferogram to match that. And there's a tool inside of GMTSAR to do that, and I can't remember the name of it. It goes to the Nevada GNSS archive, and hopefully in Iran you have those data in that archive, and then it will pull out the data, it will do the it'll do the correction, and then fix your interferogram. And then parallel, that's another great question. So far, there's nothing really in parallel, but except that since you had so many interferograms, you had hundreds or thousands, I can't remember, you could just run each one of them independently in a different, window. There's a parallel package that you can get for Unix that will do that for you. Keep always 7 or 8 in running simultaneously. And the SBAS can be really, really slow. I don't know if you noticed that, but so those are sort of the answers. Maybe Anne has something to add.
I can add a little bit on to 3. I think right now the GMTSAR's way to parallel is once in the batch processing, once you have multiple interferograms. So usually it's not an issue if you just have one interferogram, but if you have multiple interferogram, they will try to launch multiple jobs. So as long as you're not out of memory and there are multiple CPU and each of them just to work on one at a time. But definitely it's just another design, and I think there's some potential to add the parallelization, but then it's kind of, we have to redesign the structure. But for the phase unwrapping snafu, I think most of the InSAR software is using snafu. So snafu has an internal switch to turn on to unwrap an interferogram using multiple CPU. I was gonna try to experiment that option to embed it into the current shell script. But if you're interested to know how to do that, please reach out to me. I have another Python wrapper for snafu that do that. Usually it runs pretty fast for reasonably coherent interferogram. I based on my personal experience, turn on the snafu code is already parallel. So just to be able to turn on the parallel mode instead of just trying to run multiple jobs is usually faster, because the phase unwrapping gets substantially slow if your image size get large. So that it's not a scalable algorithm because the nature of a L1 based L0 based problem. And so that's why if you're using parallel mode, what it does is chop off the images into multiple chunks, and then they unwrap separately, and then they do a merge. Typically, it's much faster than trying to run one single image using a single one. So I can show, if someone is interested, I can show an example how to run that, probably through the email. But I identify that I need to do multiple tests, but that's a potential feature we can add it to the shell script.
Okay, thank you very much. Just David, for the reconfirmation, you said that TH2 is not that much important in the snafu processing. Yeah, did I get it right?
Oh, it is. I guess TS2 or one of those will mask the phase before you run the SBAS. So it is sort of important that you get one of the, but numbers like 0.1 are typically good. And 0.7, if you use 0.7, there wouldn't be any data left. So I don't know where it comes from. Yeah.
Okay. And if in an area there is no GPS station to lock actually to tie your InSAR results to that, if we don't do the zero referencing to the GMTSAR results, what would be the problem then? Are the results still have the ambiguity of 2n pi or something like that?
That's the problem. Every unwrapping will have a 2n pi ambiguity, and if one of the interferograms is raised by 2 or 4n pi and you put it into the time series thing, it'll create a step there or something.
So the idea is InSAR measures relative motion. So that fact won't be affected if you add a constant 2 pi, right? And so that's just usually if there's no GPS data available, the best practice you can guess is definitely you don't want to pick a reference station in the fast deforming region, right? There are probably relatively faster moving if it's an aquifer, trying to pick something outside the major aquifer where you are expecting deformation. And so then you're still measuring the relative motion. And your final map, if you do the zero referencing, would be still, the relative motion is still accurate. It's just that you couldn't account for maybe a small motion that occurred as your reference location. And when no GPS station available, no matter what software you use, you're gonna miss that absolute value as a reference location. And another note I would like to add when you're picking the reference location is that when you're trying to pick a reference location, you kind of want the noise as a location is relatively reasonable. You don't want to pick in the middle of a forest area. So a good location is with a relatively small motion. It doesn't need to be completely free, but hopefully if you pick in the middle of the volcano, then it just looks like you're picking the reference location in a moving car. So the relative motion is correct. It's just the value well looks a little odd in that reference frame. And so when you're picking a reference location, you would like to pick somewhere with a relatively small motion. And also, usually it works better if you're picking locations with relatively sparse vegetation in a relative sense. So it doesn't suffer from a lot of decorrelation, and also relatively flat so that you don't have some topographic correlated noise there, because any errors that affected your reference location, if it's a particularly noisy location, you pin to that location, then it actually affects a lot of the non-referencing region. And so.
Yeah, okay. Thank you very much. Thank you. I will reach out to you and for more discussion about it. Thank you very much.
Thanks.
And our next speaker is InSAR time series analysis for monitoring the Tobash landslide from Mohamad, Hossein, Talebi.
Hello everyone, I'm Mohamad Hossein Talebi. You can call me Hossein. I've been working on landslide study, and for 2 years I've been working with InSAR. Today I talk about time series InSAR analysis for the Tobash landslide. At first, I'll briefly talk about the Ridgecrest earthquake in 2019, which I've done in the GMTSAR course. As you see the description of this earthquake and rupture area. I'll do the InSAR, and you can see the correlation, and here is the dark area represent the rupture area, and you can see the fringes here for the red area, which represent displacements. I calculate line of the site of displacement in the radar coordinate and according to the Google Earth, and you can see the displacement in the blue and red color, which red color represent toward to the satellite, and blue is away to the satellite. I also do time series analysis with 21 data, which more than 100 pairs of interferogram, and I choose this data as a master image. And you can see two correlation map. One is before the earthquake, and this one is during the earthquake, and you can see here the dark area, which represent the rupture, and we have deformation here. And also rock phase before the earthquake, and also let me show it with laser point. Before the earthquake and during earthquake, the InSAR, you can see here lots of fringe, and the order of line represent the toward or away the satellite. Here is actually away, and here is toward. And here is unwrap phase before and during the earthquake, and we in here I used to F1 and F2 subsurface and merge it in the GMTSAR. And here is the geocoding velocity of this earthquake for F2 and F1 subsurface, and I also calculate the history point of here for the time series. And as you can see, this period of time we saw a drop in displacement and showed the earthquake. Here is a little uplift. Maybe it's noise, but maybe it's the period activity of seismics. Now let's dive into our main project, and is related to the landslide is located to the Iran and near the Shiraz. And the formation of a landslide is mostly weak limon and a little bit limestone, but the landslide is mostly formed by weak marl. I use the burst instead of the whole SLC, and because my area is a little small, and one burst covers full my area of interest. And you can see the ascending and descending orbit, and use both of them for actually compute the horizontal and vertical displacement. I use data from beginning of 23 to the end of the 24 for both ascending and descending, and I use all of the data are available in Sentinel-1A. Here is the perspective of the landslide, and as you can see here, we saw continuously shown in the year, and I show the line of sight of the ascending orbit, and in the north-east and vertical horizontal, which this angle represents the azimuth angle, and this angle is the inclination angles. Here is the azimuth and incidence angle for the ascending, and here is for the descending. The is calculate from the east axis counterclockwise. As you can see, here is 100, and here is minus 100, and the incidence angle is it's about 38 degrees. Here is the average spatial coherence for the ascending and descending orbit, and you can see most of area has a high coherence. And I also do something to see the correlation between the slope direction and the failure area. This failure area is by the observation and also InSAR analysis. And as you can see, we have a correlation with the failure area with the slope directions. You can see the interferogram network for the ascending for these 2 years. And as you can see, most of the line has a high coherence, and just one of them has a lower than 0.7. And here is the velocity of our area. I use a mask with the shapefile and crop my area. And you can see the failure area with blue point. And I also choose the reference point. Here is the limestone, and we saw here there is no deformation because of the rock formation, and the slope is here is not very too long. And here is the descending orbit. As you probably see, the descending orbit has no contract like ascending because of the actually the vector of the line of sight and the vector of the displacement. And here we have very high coherence. With both of the ascending and descending, I calculate the horizontal and vertical displacement, because as you know, in the landslide, it's very important to the type of the landslide and find the failure area. Here is we saw a very high deformation in the S direction, and because this area has a gentle slope, and the whole area has a settlement, and because the mall has low permeability, and when it rains, it's a flow, and we saw the displacement in this area. I also do uncertainty with velocity standard deviation, and as you can see, our area standard deviation is less than a millimeter, and it shows our result is reliable. And I also do something interesting. I draw a displacement over these 2 years, and I also show the rainfall over 2 years. There's just two rainfall more than 50 millimeters, and as you can see, after these two rainfall, the rate of displacement increase. And also another thing I've done is that the correlation between the displacement and the rain days per month. As you can see here, the rate of displacement is higher than this time, and because the actually rain days is higher than the this time. So I think the trigger of the landslide is mostly about the drainage system, and we have to redesign the drainage system to figure out the behavior after the variable drainage, what was happened. So we suggest that actually design a new drainage system, and actually monitor landslide again. Thank you for your attention. I'm happy to answer any questions.
Yeah, that was a nice talk. Sentinel is really a challenging SAR to use for this because the pixels are sort of big and your area is really small, but you were able to get a pretty good signal out of it, which is good.
Thank you.
This is great. So we'll move to our next speaker. And
excuse me, can I ask a question? I have two landslides here. Can you see my screen?
Yes.
But when I work with InSAR, not have a great result. These two landslides, and it's suddenly, and maybe with NISAR we can do something like that, yeah, or no?
So it kind of depends. So the limitation you have with Sentinel, there's still some limitation with NISAR, but it's just when you have NISAR, the L-band data, and when you have like how big is too much of a surface disruption to lose coherence, they have a different criteria. So NISAR is more tolerant to a relatively larger disruption because its whole wavelength is 24 centimeter compared to C-band is 5.6 centimeter. So it's just how big of a change the two sensor perceive as too big to lose the coherence is going to be different. That's why it might work better in general in region with landslide, rapid landslide, probably NISAR are going to perform better. But we never know typically. every time I have a new area, we have a new data, I process a couple interferogram, I look at them, kind of compare them, then they give you an idea about, look at like their quality difference directly. Yeah, we won't have
Thank you.
NISAR data for the first 3 months, but hopefully towards the end of the year, you're going to start to have these streams of data available.
Thank you.
Yeah. Yeah. And let's go to the next speaker, Alister Teow, utilizing InSAR for rapid nature hazard assessment in Hawke's Bay, New Zealand.
Right. Hello everyone. I'm Alister. I am a geotechnical engineer, so it's a bit different from everyone else. So I'm quite interested in things. I'm quite interested in landslide, which is part of my everyday day-to-day job actually. So let me make the screen bigger. Here we go. Right, so I'm kind of interested in using InSAR for more of a rapid hazard assessment to try to see where the damage is. So a bit of context, there is a massive sort of cyclone that sort of struck the east coast of North Island, New Zealand, about 2 years ago. It caused a lot of damage, 14.5 billion New Zealand dollars, and there is somewhere along the line of 100,000 landslip sort of map. So I'm quite interested, more of a feasibility type thing. I'll be able to use InSAR to help determine the extent of damage. So in order to do that, I use 2 images. So I use 2 descending images. So I before and after. So before it is a few days, 4 days before the storm event, and after it's about 7 days after the storm event to see what we can see and what the result is actually. So the processing I use is a GMTSAR P2 processing, and I use the SRT and 1 second digital DEM to kind of correct for the topographic phase. I didn't include any map of where the location of my site interest is. So and my presentation. So what I'm looking at is a site in Napier right here. So this is the east coast of New Zealand, and the storm sort of track from north of New Zealand and kind of hit Napier and Gisborne type region. If we sort of zoom into it, there's a bit of context really. This is really good. You can see all the spots on all that. It's actually all landslides. So they're sort of spotted around the country, around the east coast, and there's heaps of them. So I'm quite interested, what can we see using the InSAR data, whether we can see anything or not. All right, let's have a look at the results. So what we can see from the result, it is the coherent, it's not the best. There's a lot of speckles from the oceans, it's what I expected. There's the coherent on the grassland area, it's not the best too. I initially thought it would be pretty good coherence because I sort of thinking that maybe sort of all this debris is kind of full of water. Maybe it will show as a bright spot in the amplitude phase, but I'm not really sure how that affect the InSAR point of view. So I guess what you can see is the kind of like a bit of tight fringes around the mountain ranges, sort of west of Napier, which is the city, and it's sort of consistent with what we see on the aerial photograph. But on the S Valley, it's a hilly region too, but much more grass cover. You don't really see, it's not clear if there's any damage or not on the InSAR data, which I find quite interesting. So I guess that's the wet phase. Let's quickly look at the line of sight, the unwet phase, sorry. So what we can see is we can see that around Napier region, there is about 30 mils of movement toward the satellites. In the surrounding region, so that could be silt inundation from the flood event. This is sort of in a ballpark-ish figure, approximately what I sort of observe on site when I sort of go to site and do help them maybe the damage. So it sort of makes sense. I guess in terms of what we see the lands in the mountain ranges or the landslides, it's 100 mil. So I mean, I would tend to expect a lot more inundation, a lot more debris. So I was expecting within the meter range for this sort of region here. I guess for a bit of context, the mountain ranges is really good coherence, and I guess the surrounding grass area is not the occurrence is not the best. I imagine the mountain ranges is pretty angular, as it's mostly rock cover, so it's quite nice. But the grass area is a bit of an interesting one. So I guess a bit of a summary. What I sort of a bit of a summary. I found that maybe because maybe the Sentinel data might not be the best fit for this case here, because I find the spatial resolution of the Sentinel data to be quite large, or too bigger than my landslide size itself. So therefore, you can't really detect anything. So it's everything sort of grouped together. So what I was hoping for initially is I was hoping to see sort of individual sort of landslides where you have sort of a nice sort of deformation area on the top of the landslide, so away, and at the bottom is you sort of see more of a reddish color where it's more inundation. So I was hoping to see that, but I didn't really see it here, which I thought is quite interesting. I guess it is again, the landslide movement is quite more clearly evidenced in the mountain ranges region, but not so in it sort of S Valley, which is sort of grass cover. So it might be due to low coherence, perhaps. I'm not entirely sure. I guess a bit of further works be quite interesting to see what happened if you do ascending orbit images and sort of compare it. Be quite fun thing to do. So maybe we get different results. We could also do what many other did in the presentation, is you do time series analysis to see these kind of quantify the type of movement. I guess I could also try to play around the default max parameters. So I know you mostly use it for earthquake, but maybe because I was expecting quite a big inundation for what I observed on site, maybe that could change things from the unmapping phase, but I'm not entirely sure. I guess and phase filtering too. But again, hopefully by reduce amount of multi-look on it, maybe I can see individual landslide more clearly. And yeah, I think that's about it. So yeah, it's been really fun. I learned a lot in a short amount of time. So thanks to everyone. Thank you. Let me short share my screen.
That's great. What time is it in New Zealand now?
It is. I'm actually based in Manchester right now, so it's
on the other side of the
other side of the world. Yeah, so I moved to Manchester. Yeah, from New Zealand. Yeah.
Yeah, your summary about having the pixels be too big for Sentinel. I guess you just have to find a saddle. InSAR will be much smaller pixels, so it might work better, and especially L-band might be better. But it's a challenge when you want to look at something that small. Yeah.
Yeah, for sure. Yeah.
If you want higher resolution, I don't think the descending path gonna make a difference because it's the same resolution. And so usually when switching from ascending to descending, I noticed the difference when the tropospheric noise is play a role, because for my West Texas data, ascending was acquired in late afternoon, descending was acquired in the early morning, and then the tropospheric noise is less in the early morning than late afternoon. But so that won't probably help with your particular okay, but the line of sight viewing angle is different, so that may change slightly on the sensitivity of the motion. But if you want a higher spatial resolution, probably I recommend you look into maybe Terrasat X data. That's probably so far one of the higher resolution data product you have, but it's X-band and the decorrelation, these kind of issue gonna be worse. But typically, if you're interested in finer scale feature, Terrasat X does has a much better spatial resolution than Sentinel.
Yeah, for sure. Well, thank you very much. Yeah.
And if you have a larger movement, you might not even need the coherent phase. You could just use the amplitude image and do the pixel tracking.
Yes, yeah. I need to look more on pixel tracking. That's one thing I learned today. That is quite interesting. Yeah. All right, thank you.
Yeah. And we have our last speaker, and Bagas Triahan Manhana. And the talk is a Sentinel-1 InSAR data processing to monitor surface change. Bagas, are you here? Maybe we lost one student. Let's see if he's on the speaker list. Maybe the student is not available for some reason. So if that's the case, then it's probably the end of our session today. And it's a really great pleasure to work with everyone here, with the instructor team and with the student.
Yeah, thanks, Anne. Thanks, everyone. Are we gonna, can people submit copies of their presentations to the Moodle site?
Yes, it's required, I think, for them to receive the credit. So for the student who present, please still remember to submit your presentation from Moodles because that's the only way to get the certificate.
Yeah, I'd like to look at them again. They're really good. Thanks.
Yeah, Roger, do you have anything to add? I see you turn on your camera.
No, nothing. Just these were great presentations. I really enjoyed listening to them all and learning what everyone's been working on over the last few weeks.
Yeah, I had a lot of fun troubleshooting issues and interacting with students, and so thank you, everyone. So other than that, we conclude our session today.
Thanks.